Okay guys, welcome back. So in the last video we talked about the resistors in series or series resistors. So in this video I'll be talking about resistors in parallel. So resistors in parallel is equally important in its concepts as resistors in series, because these two points, so these two videos, the concept that you will be learning in these two videos will be the base for the other videos and the problems of you'll be solving in current electricity. So most all of the theories are based on and all of the solutions for the problems you will be facing in current electricity will be based on resistors in series and resistors in parallel. So I already explained to you about the resistors in parallel, the general equation that we can derive, and I explained to you that using a sample example as to how resistors in parallel is important in determining the other quantities in current electricity. So if you are not watched that video, I invite you to watch this video, because although there is no correction between these two videos, if you have watched these two videos, if they have watched both of these videos, it will be of great importance to you, so that you can maintain a flow in the current electricity, and hence you can understand the concepts very easily rather than going through individual lessons. Alright, so in this video I will be talking about resistors in parallel. Alright, so resistors in parallel. So resistors in series was a concept in which these resistors were constructed in a single line. So what I meant by a single line is that they should not be actually in a single line. What is actually important is that we are using the same current. But in resistors in parallel, what actually happens is that we are using not the same current, the current differs, but we are using the same voltage or the same potential difference. So I'll draw a simple example of resistors in parallel, and I'll then deduce a simple relationship using the practical example I have drawn. Okay. So let's take an apparatus to be like this, a circuit like this. So the first circuit will be like this. This is a wire connected to a resistor of resistance R1, and the two ends of the wires is again connected to another wire who's connected to a resistor of resistance R2, and these two ends are again connected to another wire of resistance R3. And the two ends of all these resistors now share a common point, these 2 points. So I'll take these 2 points to be A and B, and I'll connect these A and B through a potential difference or a potential normal cell, right? Normal dry cell of voltage V. So what I'm asking is the current, what is the relationship you can draw from this V, I, R1, R2 and R3. Alright. Now, as I mentioned at the beginning of this video a little while ago, now this is the topic of resistors in parallel, right? Resistors in parallel, or parallel resistors. As I mentioned in the first part of this video, when in resistors in parallel or parallel resistors, right? So what actually happens is that, unlike in the resistors in series, the total current through in these individual resistors is not equal. What actually happens is that the voltage across these individual resistors is equal, because the voltage should be equal, because now considering this point to be C and this point to be D, VCD should be equal to VAB. So since VAB is common to all these regardless of the path, now this line, this loop, we call this a loop, right? I'll explain the concept of loop in another video. So this loop pretended to be just two connecting points to be a loop. So this loop actually has a resistance of R1, because it is connected to a resistor of R1, and assuming there is no resistance in the wires, so the total resistance in this loop is R1, and total resistance in this loop is R2, and the total resistance in this loop is R3. So all these are connected to these A and B points. So the voltage across all these resistors should be VAB. So since VAB is equal to VCD, all the voltages across all these resistors should be also V. So this is V, and this is V, and this is V. So the voltages are same, but the currents are different, because V equals IR means if the voltage, if we were to maintain V equals IR means if V is constant, I times R should be constant. I times R should be constant. So since resistance is different, for the first circuit it will be R1, so the current should be not equal, because for the second, if you divide IR by second equation, when the R value changes, I value also changes. So I'll take the current across the first loop to be I1, the second loop to be I2, and the third loop to be I3. So the current should change, because IR, since IR is a constant, and when R changes, the value of I changes. So the current through these resistors changes, but they share the same potential difference. Alright. So assuming these 2 points, I can put V equals IR, right? So when I put V equals IR for resistor 1, so V equals I1 times R1, equation number 1. V for the resistor 2, V equals I1 times R2, equation number 2. And for the third resistor, V equals I3 times R3. Now what actually happens is that I provide a voltage of V, so a current of I is generated, and this I is distributed 1 across I1, 1 across I2, and 1 across I3, right? So what actually happens is that the current that is being sent is the current that will be sending, and again when at B the total current merges, all the total current is connected together to point B to make I. So I should be equal to I1 plus I2 plus I3. So this is very easy. If you have actually watched my video, on series of resistors in series or series resistors, because in resistors, series resistors, what actually happened was that the total voltage was equal to the summation of the individual voltages. Now in resistors in parallel, what actually happens is that since the total the voltages across all these resistors is the same, the total current is equal to the sum of the individual currents that flows through these resistors. Alright, so that's very easy. So since I equals I1 plus I2 plus I3, from equation 1, 2 and 3 I can substitute the value of I1, I2 and I3, so sorry, this is I2, right? I1, I2 and I3 to here and find that. So I is equal to I1 from equation 1 is V by R1, I2 is V by R2, and I3 is V by R3, right? V by R3. So if I put this single circuit, now as I have been putting for the series resistors in series, if I put R effective, a single resistor that can replace, now this is also very analogous to the resultant force, right? The single force that can have the same effect as the set of as a set of forces. So the effective resistance is also like that, a single resistor that can have the same effect as the effect produced by a number of or a set of resistors. So if I connect this with for a voltage of V, and a current I is flowing through this circuit, what I can say is that V equals I times R effective. So I is equal to V divided by R effective. So I is equal to V divided by R effective. I can substitute that here. So V divided by R effective is equal to V by R1 plus V by R2 plus V by R3. And since the potential difference across these circuits is not zero, I can divide the whole equation, both sides, by V, so that the numerator of all these fractions will be 1. So I'll get the equation, general equation for the effective resistance, 1 upon R effective is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now as in the video, as I explained in the series resistors, I can write the general equation for n number of resistors. Now this is for 3 resistors. If it were 2 resistors, it will be 1 upon R1 and 1 upon R2. For 3 resistors, it will be 1 upon R1 plus 1 upon R2 plus 1 upon R3. For n number of resistors, the effective resistance 1 upon R effective will be sigma from I equals 1 to n 1 upon R. So what actually happened when the parallel resistors were in series, were that we took the equation, right? We took the sum of the resistance, right? So this was from the final video, right? From the previous video. So R effective when it was in series was R1 plus R2 plus R3. So that it was actually the sum. Now what actually taken when it is in parallel is 1 upon the sum, right? 1 upon R1, 1 upon R2 and 1 upon R3. Okay, so that's the resistors in parallel. So what actually happens is that you can calculate the equivalent resistance or the effective resistance of a series resistors in series and resistors in parallel. So this is the basic concept actually in the course of theories on current, resistance, voltage and other circuits. So these two videos will be of utmost importance and of equal importance, utmost importance and equal importance to the next concepts I will be talking about in current electricity. And thanks for watching this video and see you then.